Hello everyone, let's pick up in 4.2 where we left off. We had just talked about lower and upper sums based on using rectangles, and it kind of relates to the Archimedes principle called the exhaustion method, which is where they were using shapes to approximate the area of a circle. Their version of the exhaustion method basically said this: as I add more and more sides to the shapes, I got a more and more accurate depiction of the area. So what we did in the last video is we used only 5 rectangles to approximate the area under a curve. But if I can break it up into more and more smaller and smaller rectangles, it should become more and more accurate. Now, if we consider this plane region here, it's bounded by a function and an x-axis, and it has left and right boundaries from A to B. To approximate the area of the region, we need to first divide it into rectangles. Now, each of these rectangles is going to have a certain width depending on how many rectangles we break it up into. So if this width is B minus A, if I'm going to break it up into n evenly sized rectangles, the size of each of these rectangles, which we'll call delta x, the change in the x values from each rectangle to the next, will be B minus A divided by n. That makes the end point of each rectangle, it starts at A, and then it goes up by each little, what we call a partition, each little width of a rectangle to reach the end points of each rectangle until you've hit all of the rectangles, and then you should end up at B, which makes sense because if you add n times B minus A over n, the n's would cancel and you'd have A plus B minus A, which is just B. Because this function is continuous, the extreme value theorem also will tell us that somewhere in each of these rectangles, there should be a lowest value for the height of the function in that area and a largest value for the height. And now we know if we use the lowest area, that would be kind of like inscribed rectangles under the function, that should underestimate the area under the curve. And if we use the maximum area, that should overestimate the area of the curve. And those two things should give us a lower estimation sum and an upper estimation sum. And the way that this actually looks is on the next page. We can take this function, here are inscribed rectangles under the function. As you can see, the area of all these rectangles should be less than the area under the curve, but our circumscribed rectangles all give us a greater area than the function, and if you added them all together, that should be larger than the actual sum, and that means the actual area under the curve lies between these two things. Now, how do we arrive at the actual estimation for the sum? Well, we can kind of use these lower and upper estimations and then use limits as our the number of rectangles goes, to infinity. The limit as n approaches infinity to kind of get an idea of where these two things are. So find the upper and lower sums for the region bounded by the graph f of x equals x squared and the x-axis between x equals 0 and x equals 2. So how we start this is we first need to break up our area into pieces. And by that I mean we take our right bound and our left bound, 2 minus 0, which is 2, and I divide it into n pieces. So delta x would equal 2 over n. I can then use my summation notation. The left side doesn't start at our i's, because if I'm breaking it up into, instead of starting at 1 and going to the end point, if I'm using the left side, I actually start at I minus 1, and then I continue until I get to the last piece, minus 1. So for our lower sum here, we'll have I equals 1 to n of our lower estimation, because this is increasing the whole time. The left side gives us the lower estimation. The minimum, which we call mi, times our width. But if I use my substitutions, I know that on the left side is my low end. So I'll have I equals 1 to n of what we call the evaluation of our function. So that would be f of 2 times I minus 1 over n times the width of our rectangles, which we know to be 2 over n, as defined before. Now, what is our function in particular, x squared. So this gives us I equals 1 to n of 2I minus 2 over n squared times 2 over n. Technically speaking, what I can do is I can pull the 2 over n out front and square it. So that would be 4 over n squared times 2 over n, which is 8 over n cubed, which is not affected by our summation. And that leaves us with the inside of I minus 1 squared. And then I can expand that to get 8 over n cubed times the summation from I equals 1 to n of I squared minus 2I plus 1. And if I break those all apart, 8 over n cubed, I equals 1 to n of I squared minus 8 over n cubed from the summation of I equals 1 to n of negative 2I minus 8 over n cubed from I equals 1 to n of 1. Now there's more things I can pull out here to deal with this. This is now 8 over n cubed. My pattern for I squared is again n times n plus 1 times 2n plus 1 over 6. I'm going to actually pull out the 8 over n cubed out for all of these. My pattern here for the negative 2I will be negative 2 times n plus 1 over 2, because that's the pattern for I. And my pattern here will be, this will be a plus. Just n, because when you're adding 1 over and over n times, it produces n. And then from here, it's about cleaning everything up that you can. I'm going to go ahead and simplify for you. The n, this will multiply to be an n cubed, but when you do clean it up, it ends up being 8/3 minus 4 over n, when you distribute it through to the second one, plus 4 over 3n squared. Now, why is that the case? Again, if we had cleaned up the outside, these all could have had multiples of 2, or they could have been, when you multiply these all out, they combined the other terms. And when you combine your like terms. Now, what that means though is that this area depends on what you pick for n, and n kind of depends on how many rectangles you are going to be creating. Now, if you do the right side instead of the left side, you end up getting something very similar. You end up, so this is the smaller one. Your larger summation ends up almost exactly the same, but instead of minus 4 over n, it adds 4 over n. If you do the same thing, but instead of I minus 1, you just put I there, you end up with this term. Now, what you'll notice, though, is that these look very similar, but the lower sum subtracts off a piece that the upper sum adds on. It's not a coincidence that those look the same, though, because we know as n goes to infinity, based on our rules from previous sections, these two things will go to 0, and that will tell me that the lower limit is 8/3 and the upper limit is 8/3, and if you're sandwiched between the two of them, the total area is 8/3. And that leads us to a very interesting definition of our lower and upper sums and how they affect our area. And we'll look at that on the next page. Formally, let f be continuous and non-negative on the interval ab. The limit as n approaches infinity of both the lower and upper sums exists and is equal. And therefore, the limit as n approaches infinity of this lower sum times delta x and upper sum is equal to the general limit as n approaches infinity, where delta x is the width of our partitions, and f of little mi is our minimums, and f of large mi are our maximum values on these. Now, how do we get this third one when we said these two limits are equal? Well, the actual limit of our function I mean, these are all the same, right? If we said these two limits are the same, those represent the lower and upper functions. And technically, we could make the argument that the actual area under the curve is equal to those two, because if I'm squeezed by the squeeze theorem between two things that are equal, I must be equal to those two things. So what that tells us is that the area of a region in the plane, generally speaking, is the limit as n approaches infinity of the sum as I equals one from the sum from I equals 1 to n of any height value in that little region of a rectangle times the width of the rectangle. Which means, technically speaking, you could take the limit of the lower sum, you could take the limit of the upper sum, or you could even, say, find the midpoint value of each of your rectangles and plug that in. So if we wanted to find the area of a region bounded by the graph f of x equals x cubed and the x-axis between 0 and 1 are vertical lines, we could do it by using this limit rule. Now, what do we know? We know that means I can choose any I, which means just choosing regular I would be the easiest. So if we took the limit as n goes to infinity of I equals 1 to n, now we know this is f of I, or f of xi, times delta x. We know that we're taking our delta x is 1 minus 0 over n, which is 1 over n. And that means our f of xi should be f of 1 over n, which in this case would be I over n. So this is the limit as n goes to infinity of the sum from I equals 1 to n of f of I over n times 1 over n. Now, since this is x cubed, our function, when we plug in I over n in, we get the limit as n approaches infinity from I equals 1 to n of I over n cubed times 1 over n, which would really be I cubed over n to the fourth. And what that means is, again, the only thing affected by this is I, which means that 1 over n to the fourth can come out front. The limit as n approaches infinity of 1 over n to the fourth times the sum from I equals 1 to n of I cubed. And using our pattern from the very, very beginning of this, we know I cubed ends up being n squared times n plus 1 squared all over 4. And what happens when I cancel these out? N squared divided by n to the fourth here will reduce. So this is the limit as n goes to infinity of n plus 1 squared over 4n squared, which is n squared plus 2n plus 1 over 4n squared. And if I separate each of those, that's 1/4 plus 1 over 2n plus 1 over 4n squared. But I'm taking the limit as n goes to infinity. And as these two n's go to infinity over here, these two things will go to 0, so the whole area is 1/4. So what that tells me is that the area under the curve x cubed from between 0 and 1 actually measures exactly 1/4. And this is kind of where the power of these summations comes from. And while if you're trying to measure a finite number, the midpoint is usually a better place, a more accurate one to do. Generally speaking, like I said, it doesn't matter if you're taking the limit as n goes to infinity, they all end up being the same. So it's usually easiest to just take what we call the right end point, because that means that you're just plugging in I over n each time for each of these values. And eventually, 4.3 is more of the same, but eventually, starting in 4.4, we're going to start to learn easier ways to evaluate this besides the limit, much like how we started our derivatives with limits and then eventually learned other techniques that are shorthand methods. But this is all for 4.2.